Methods of moments estimation is going to be a general purpose estimation technique that functions by trying to set theoretical moments equal to sample moments. And so ultimately, it's going to allow us to discover estimators for any parameter that we care about by setting some things on our theoretical distribution equal to some things in our sample distribution. It's a fairly effective technique for working through this, and the actual math that's required to derive these estimators tends to not be too involved. So methods of moments estimators are general classes of estimators. They match these theoretical and sample moments for arbitrary distributions. And so we'll have to discuss what each of these different components actually means here. So what are we thinking about when we're thinking about moments? Well, suppose that x is a random variable and it has some known distribution, or at least it's a distribution that is known except for its parameter values. The kth population moment, or sometimes just the kth moment of x, is defined to be this quantity here. So we'll use mk to denote it, and it's the expected value of x to the power of k. Right? And so, for instance, the first moment is the expected value of x, the second moment is the expected value of x squared, and so forth. Okay? And so we can define this for any value of k. And so if if x is a continuous random variable, and it's got some probability density function f of x here, then what we can say is that the expected value of x to the power of k is the integral from negative infinity to positive infinity of x to the k times by its PDF dx. And so given a probability density function, we could work out the kth moment. Now, if we have a finite sample taken, and that's going to give us these observations, say x1 up to xn, right? And we'll treat these as being random for now because we don't actually have those values, right? But we could write them in as the lowercase values once we do. Well, then we can take the kth sample moment, and the kth sample moment is going to be given by mk hat, right? Because it's estimating the population moment. And it's going to be the average of xi to the power of k, right? So 1 over n times the sum of xi to the power of k. And so we have these theoretical moments, right, which are the expected value of xi to the k, and the sample moments, which are the average of xi to the power of k. And so the first sample moment is the sample average, and sort of so forth, right? This is going to give us a sample estimator for mk. Now, why is this useful for us? Well, the method of moments estimators are going to equate these two sample and population values, and by doing that, that's going to allow us to solve for estimators of any parameter that we might care about. So if we think that x is parameterized by some parameter theta, right? Theta might be one single parameter. It might be a vector of parameters. It's the same process no matter what. Then in general, all of the population moments, or most of the population moments, are going to be dependent on theta. That is to say, we can treat mk as a function of theta. And so once we know what the form is, that form is going to depend on the value of theta. Now, it should also be the case that if we knew the true value of theta, then we would expect that the population moments that come from that are going to be approximately the same as our sample moments, right? And of course, the larger our sample, the closer this approximation should be, but they should at least be close to one another. And so then what we can do is we can form what we call the method of moments estimators by combining these two different observations in order for us to produce an estimator, theta hat. So theta hat is going to be the estimator that solves for theta if we set our sample moments equal to our population moments, right? So we have a function of theta, we set that equal to our sample moment, and then we solve, and whatever the value that we're solving for, that's going to be theta hat. Okay? So if theta is a p-dimensional parameter, right? So if there's p components of it, then what we do is we take the first p theoretical moments that depend on theta, and then we solve the following set of equations. So we take the first theoretical moment equal to the first sample moment up to the pth theoretical moment equaling to the pth sample moment. We solve these equations simultaneously for the value of theta, and whatever that is gives us theta hat, which is going to be an estimator we can use to actually estimate values for theta. Okay, so let's take a look at some examples here. First, we're going to start with perhaps the most straightforward version of the method of moments estimators, and that is taking x to be the normal with a mean of mu and a variance of sigma squared. And what we want is the method of moments estimators for theta, which is both the mean and the variance. And so in this case, right, the dimension of theta is 2. And so what we need is we need two equations that are going to depend on the means. And so we start with always our first moment, right? So m1, which is the expected value of x to the power of 1. And this is just the mean of x, right? And so we know that that's just going to be mu. Our second equation, we can find m2, right? m2 is going to be the expected value of x squared. And now, importantly, this is not going to be the variance of x, right? But instead, this is going to be the variance of x plus the mean squared, right? And why do we get that? Well, remember that we can always write the variance of x as the expected value of x squared minus the expected value of x squared. And so then solving this for expected value of x squared, this is our second moment here. Okay, and so then we can rearrange, and what that's going to tell us is this has to be sigma squared plus mu squared. Okay, and now we need our sample moments as well. So m hat 1, this is going to be 1 over n, the sum from I equals 1 to n of xi, right? Which we could just write, that is our sample mean, x bar. And m hat 2 is going to be 1 over n, the sum from I equals 1 to n of xi squared. Okay, and so now we have all of the components here. What we need to do is we need to plug in a value mu hat and sigma hat squared that is going to solve 1 equals, and I'll mark this as A and mark this one as B, right? We're going to set 1 equal to A, and we're going to set 2 equal to B, and we're going to solve. Okay, and so doing that, right, we're going to have mu hat is going to have to be equaling to A, which we found was x bar. Okay, and then for 2, we're going to get sigma hat squared plus mu hat squared is going to have to equal 1 over n, the sum from y equals 1 to n of xi squared. And so we've already actually solved for what mu hat is, right? So then we can use this to simultaneously solve this second equation for sigma hat squared. So sigma hat squared is going to be equal to 1 over n, the sum from I equals 1 to n of xi squared, minus mu hat squared, but we know that mu hat squared is x bar, or so that mu hat is x bar, so that's going to be minus x bar squared. And actually, we could leave it like this, right? That gives us an estimator for sigma hat squared and an estimator for mu hat. But we can also write this as 1 over n, the sum from I equals 1 to n of xi minus x bar squared. Okay, and so this is similar to our sample variance here, but it's not quite the sample variance, right? This is not dividing by n minus 1, it's only dividing by n, okay? And so following this procedure, we get our method of moments estimators here. Okay, and so let's walk through that again, step by step, just to make sure that it is all clear here. So to find these method of moments estimators, right, the first thing that we note is that theta is two-dimensional, and so we require two different moments that depend on theta. We can take the first moment to be the mean. The second moment is going to be the variance plus the mean squared. And so then we set the expected value of x equal to m hat 1 and the expected value of x squared equal to m hat 2. Right? Doing this for the first moment gives us that mu hat has to be equal to x bar. Right? And so that solves that first equation there. For our second equation, right, we have that sigma hat squared plus mu hat squared has to be the sum of xi squared over n, right? But we can rearrange this because we know that mu hat squared is going to be x bar squared, and so then we subtract that over to the other side, and that gives us this sigma hat squared minus, or the second sample moment minus mu hat squared, and so then that's 1 over n sum of xi squared minus x bar squared, right? And so you could leave it like this. That's a perfectly valid expression, but if you factor down this expression, you actually get sort of this nicer format for it here. And the reason that we like that is because we can actually write that in terms of the sample variance as well. So that's n minus 1 times the sample variance divided by n, right? So it's the sample variance, but instead of dividing by n minus 1, we divide by n. So the method of moments estimators for the normal distribution are going to be the sample mean, and then the average squared distance from each point to its mean, right? That gives us the estimator for the mean and for the variance. It's the sample value for the mean. It's not the sample value for the variance. Now, take a second example here. X is going to be a uniform on negative a to positive a. And what are the methods of moments estimator for a? Okay, and so again, we need to end up coming up with enough moment equations that depend on our parameter in order for us to solve for this. Okay, and so we're going to start with the first moment, which is the expected value of x. And if we think about, well, what's the expected value of x? The expected value of x in the case of the uniform is a plus b divided by 2. And so that's going to be negative a plus a divided by 2, which is 0. Okay, and so this is a problem because 0 does not depend on a. And so this equation is actually not going to be useful for us to solving our method of moments estimators, right? And so instead we should go to look at our next moment. So what's the expected value of x squared? The expected value of x squared is always going to be b minus a squared over 12. And so that's a minus negative a squared divided by 12. A minus negative a squared is actually 4a squared over 12. And so that's a squared over 3. Okay, and so now we have an equation. We have our one equation here that depends on a. Okay, and so what we need to do is we need to set then m2 equals m hat 2. Right, and this is going to tell us that, say, a hat squared over 3 is going to equal 1 over n, the sum of I equals 1 to n of xi squared. Okay, and now we can rearrange and solve for what does a hat have to be. A hat is going to be the square root of 3 over n, the sum I equals 1 to n of xi squared. Okay, and so this gives us an estimator for the value of a here, right? It is going to depend on the second theoretical moment because the first theoretical moment happens to be a value of 0. Okay, and so we need to make sure that we have enough equations to solve for this. And in this case, that meant using the second theoretical moment, even though our parameter is only one-dimensional. Okay, so theta is one-dimensional, so we require a single moment. The expected value of x, that first moment, is 0, so it does not depend on theta. So we get the second value here, which is going to be the variance because the mean is equal to 0, right? And so that gives us a squared over 3. If we set the second moment equal to the second sample moment, and then we solve for what a hat would have to be, that gives us a hat is the square root of 3 over n, the sum of I equals 1 up to n of xi squared. And so then given any sample, if you wanted to, you knew it was coming from this uniform negative a distribution, you want to estimate what a is, you can use this estimator here. Right? So that's always going to give you a valid estimator. Let's take a look at another example here. X has a probability density function that's given by f of x is lambda e to the negative lambda x for x being greater than or equal to 0. And what is the methods of moments estimator for lambda? And so if we wanted to solve this, right, we need to get our first moment. And so m1 is the expected value of x, right? We're given our density function here, and so we can take this. This will be the integral. It's defined only on the positive x, right? So that's 0 up to infinity of x times lambda times e to the negative lambda x dx, right? And you could do, say, integration by parts here, and what you're going to find is that this solves down to 1 over lambda, right? And so we'll sort of skip through the calculus steps here, but ultimately this is going to solve to be 1 over lambda. And so then if we want to set m1 equal m hat 1, right, that's the same thing as saying, well, 1 over lambda hat is equal to x bar, right? And so then solving for lambda hat is 1 over x bar. So it's the inverse of our sample mean, right? That's what our method of moments estimators is here. And so in this case, right, as long as you can solve through this integral, then working out what the method of moments estimators is after that point is not too challenging. So setting this up again, right, we find the expected value of x is this integral here that solves down to 1 over lambda, right? And so then setting expected value of x equals 1 over lambda hat, which is x bar, then we solve for lambda hat has to be 1 divided by x bar. Okay. Now, if we suppose that we go out and we perform an experiment and we collect 5 pieces of data, right? So we have the observations being 0.008, 6.451, and so forth. We want to estimate the value of lambda, right? Then how can we do this? Well, the first thing that we're going to do is we know that lambda hat has to be 1 divided by x bar. And so then if we calculate x bar, which will be 1 over 5 times by the sum of all of these values, right? So that's that 0.008 plus so forth through all of the values here, 3.148. Then we can plug this x bar into that, and that's going to give us an estimate for the value of lambda, right? And so here we calculate that lambda hat has to be the inverse x bar, and so the observations here give us x bar of 3.1848, and so as a result, lambda hat is going to be 0.3139915. Okay, and so this allows us to estimate lambda even if we don't know anything else about this distribution other than its density, right? And so we know that that's what its density is going to be. We can end up getting a value that estimates what lambda has to be based on some observations from it. Okay, so when we're thinking about the method of moments estimation, right, it's this technique that we always find our find our theoretical moments, set those equal to our sample moments, and solve these equations. Right? And so we should think about sort of what are the properties here, what are the considerations we need to make. One benefit to it is that they tend to be easy to find. Right? So the actual math does not tend to be too involved, at least compared to other estimation techniques. They also don't make very many assumptions regarding the data. We need to have the correct forms for the moments, but that tends to be a fairly weak assumption relative to other techniques that might assume stronger characteristics. Even when we do make these assumptions, they tend to be fairly robust to them. So the estimators that we get tend to work fairly well, even if we don't get the correct distributional assumptions, for instance. However, method of moments estimation is not typically going to be the most widely used technique for estimation. Sometimes it is, right? So we saw in the normal case, the method of moments estimators for the mean is actually going to be x bar. But that's not always going to be the case. So the method of moments estimators for the variance is not going to actually give us the same variance technique, okay? And there are three primary drawbacks to these estimators, right? The first is that it's not guaranteed that the method or that the population moments actually exist. So there's not a guarantee that the expected value of x or the expected value of x squared or the expected value of x cubed or so on are actually convergent integrals. And as a result, we don't even necessarily have population moments. And without population moments, you can't perform this type of technique, right? So you can't use method of moments if the moments do not exist. Now, this tends to not be a huge problem in practice, but it is something that we need to contend with. Now, the other thing to note is that the method of moments estimators tend to be biased, right? And so if you calculate a method of moments estimator, there's no guarantee that that's going to be an unbiased estimator. And for instance, we saw in the case of the normal variance, right? The unbiased estimator for the variance is s squared. However, if you look at what the method of moments estimators is for the normal variance, you get 1 over n times by that variance term. And so that is going to be a biased estimator of the variance. Now, again, sometimes taking biased estimators is totally okay, right? Sometimes they're actually going to perform better, but it does mean that we don't get this property, which is very often a desirable property. The other point, and this is probably the most important point, is that it's not even guaranteed that they're going to be valid estimates. And so what do we mean by that? Well, we might get negative variances, or we might get proportions that are greater than 1. So there's actually no constraining the method of moments estimators to have to fall within a valid range. And so this can lead us to estimates that are totally nonsensical for the given scenarios. And that's not going to be super ideal. And so in those situations, it's not clear necessarily what to actually do. Right? If you estimate that the proportion has to be 1.5, what is that actually telling you about things? Right? And so the method of moments estimators, while they have certain desirable properties, and they're especially easy to work with mathematically, they do have these drawbacks as well. And so there tends to be sort of other estimation techniques that are often used, but the method of moments estimators are, again, robust enough in certain settings, and they also provide us a really strong foundation for thinking about general purpose estimation techniques. So method of moments estimation technique allows for the derivation of estimators of parameters from arbitrary distributions. Right? Any distribution you can apply the method of moments technique to, and that's going to allow you to estimate out its parameters. It proceeds by equating our population moments to the sample moments and then solving for what that has to be. Once you've actually solved for the estimators there, if you go out and take a sample, you can plug in the value of your sample to derive the estimates for the parameters that you care about, regardless of what those parameters are. And the math tends to be not too involved to work through this. However, there are some pretty major drawbacks of the methods and moments techniques which limit their real-world applicability.